Hi, my name is Siegel, spelled C-I-G-O-L. You can find me on Kickass Torrents, kat.cr. Um, I'm going to go over how I got into Hopper. Hopper, if you understand anything about reverse engineering, you understand the basic concept of a Mach-O file. And if we open up Hopper in a Mach-O view, which is just a very basic program that parses the Mach64 header and the load commands. All the stuff below here is just an expansion on the load commands. Mach-O files are obviously set up as a header with a series of load commands. The first thing when I downloaded Hopper, obviously the first thing I want to do is figure out how does a tool used for reverse engineering protect itself from said reverse engineering. So obviously the first thing you do is you try to open it up in Hopper. Well, Hopper is basically what you see when you open up Hopper in a disassembler is a ruse. It's not real. Nothing in there is real. All the code that's in the text section that you see here, and I'll explain why this is all this code here is not real. It's fake. Doesn't do anything. It's not meant to. It's just meant to throw people off. The first thing that I noticed when I was looking at it in Mach-O view is that the dynamic loader, the DLD info, I noticed this, the binding size. Look at the size of this, 12.2 megabytes of binding info. That's insanity. That was the first thing I noticed. I'm like, why is there so much binding info? Maybe this is fake, but then if you look at the DYLD source code on apple.com, this is absolutely needed. You can't fake this. The reason I thought, well, maybe they faked it is because if you look in the text header, these offsets are goofed up. The virtual address, which the DYLD needs, is 6050, but the file offset is 2CB1. That's not right. This needs to match this in this case. So I thought maybe they were faking it. Anyways, so this is really the first thing that threw me off, is that this is massive size. So let's go down and look at what exactly is going on down here. So we want to go down into the dynamic loader info and look at the opcodes. And if we click on this, you can see it right now. It's Mach-O view is cranking super hard. And look at all this. Look at all of these commands. There's tens of thousands of commands. Now a lot of these are needed. You can see that they are actually binding stuff. But if you scroll down far enough, and you have to scroll down far enough, you start to see. Let me go in the actions. The actions just expand on what's in here. You can see here there's a lot. There starts to become this repetitive garbage. Now this is where it gets interesting. What the heck is it? What's happening here is this is telling DYLD to the dynamic loader to bind. So it's saying bind this symbol to this address, this symbol to this address, this symbol to this address, and so on and so on. And it's hard to scroll to where it actually starts because there's so many of them. Now you can see here, let me open this up. Bigger, 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 so we can see exactly what's going on here. Bind special dynamic library to the main executable. So basically what this is saying is that the dilib, it's telling the dilib, bind addend means to update or change the value, or append or add to the value at this doesn't get big enough. At the execute header, we append this value to this address, wherever this address would be. You have to go back to the opcodes and see. But basically what I'm trying to say is, oh, here it is, right here, the 6E50. Now does that bring back the 6050 here, that was the address up here of the text, right? So it's writing this value, whatever value is at 6E50, which was the beginning of the executable code, it's saying add this value to it. Offset that value at this address by this much. And you can see here they're doing a assigned integer here. But really, this all it's doing is rewriting the executable. It's rewriting the executable. So basically what's down here, all these numbers are the actual executable for Hopper. So that was the first thing I found, and I thought, wow, that's pretty darn sweet. So the first thing in what I wanted to do was get to the point where all of this executes and then stop, because at that point we should have the main executable back, right? Not so, because what happens is this is writing the executable, but it's writing it in an encrypted form, right? So let me see. Let me see here. Let me think here. I want to show you this. So let me go to LLBB. Okay, so we want to launch. Let's set the file to applications Hopper Disassembler v3.9.9.9. Now ignore this unable to find this entry, blah blah blah. Ignore that. Now we want to do a process launch stop at wait. Oh, I forgot the damn code. Process launch. Stop an entry. Wow, brain fart. Anyways, okay, so now we're in the DYLD, which is what this is dealing with right here. The dynamic loader. We're in the dynamic loader. So we want to get to the point where this executes so we can view what's in memory. And to do that, I usually will set a breakpoint by name at syscontrol, and then hit continue, hit continue, hit continue, and we're kicked out. So we want 2 continues. So we're going to 1, 2. Now if we do memory read at that address, which is we want to go to 6E50. 6E50. I just want to make sure I have that. We can see now that the data at this address is B2B315. But if we look up here at the original text, let me get to it. At 6E50. 6E50. Sorry. Getting there. You can see that the original was 4889E5 blah blah blah. Now it's B2B3. We're at the same address, 6E50, 6E50. Well, 6E51. And the reason this is not aligned right is again because he set these. See how it's 2CB1? Disalign. To fix this, all you'd have to do is go in a hex editor, change 2CB1 to 6E50, save, and then you'd be able to look at the text properly aligned. That's besides the point. What I'm trying to say here is the program has now written this, or rewritten its executable. Now what would be interesting is to dump this. Hang on one second. Okay, I'm back. Sorry. I just wanted to calculate this out so I didn't waste time. So what we're going to do is we're going to read the memory and place it into mem.bin in binary format from 6E50, and then I added 21 million bytes to it, about 21 megabytes, which is the original size of the executable. So we're going to memory read out blah 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 to my desktop. Oh, I gotta force it. It's gonna take a while to dump all that. Oh, it didn't take too bad. So no, so you can see we dumped 21 million bytes out to membin. Now this is the binary after it's been overwritten by dilib. So if we open it with let's do hexfiend. It still doesn't look like code, but something interesting happened here. We can see all of a sudden. I wonder if I can open this in. Let me try opening it in Mako view. Pretty sure I can open it in this file. Open membin desktop. I can't find it. Oh, it's not going to let me. Oh, you know what I needed to do was dump the whole file. So let's do this. Let's do 6050. Let's start from the header. Sorry. Okay, so now we should be able to open it in Mako view. File open. Membin, now it'll open. We needed that header. Okay, so now this is the dumped. Now nothing's going to really match up or anything, but I wanted to show you something. Oh, that's right, the header isn't aligned either. It's like playing. Okay, let me think. There was a lot of steps to getting this to work correctly, but I wanted to show you this. See, since these aren't set up right, you're going to see a lot of garbage, but I wanted to show you that now that it's decrypted, you can see we actually have actual Objective-C method names here. Where's the class names? Let me see, class names. All right. Sudo, all this debugger driver, document undo redo support, Hopper plugin. All of a sudden, wow, all that stuff that was missing before that everyone was like, well, where did all that stuff go? It now exists in this file. So that's interesting. Now the problem is okay, the file has been dumped, but the data there is still encrypted. I mean, if I open this up in Hopper right now, it still won't make any sense. None of the data there will make any sense. So the next thing we have to do is figure out where exactly does the dynamic loader actually start executing code. It's got to send a thread into main sometime. It's got to send a thread in there at some point. We got the catch with the binding info. So what's the next step? Well, I thought it was to call main, but there's one more shim right between the two of them, and I didn't know about this. So and some of you pros will probably be like, well, that's dumb. You should already know that. No, this is called learning. I'm learning right now, and I learned a lot. There's a point at when the dynamic loader has to initialize all the objects if they want to be initialized, and that is using the NSObject load. If you look up or Google's NSObject load, and you can see that that's a static method that gets called by the dynamic loader before anything else. And it's used to initialize static data within your class. So if you want early access to the dynamic loader, keep that in mind, programmers. You call that load command, or implement load in your class. So anyways, now I didn't know this. So of course, what do we programmers do when we run into a problem? I thought to myself, well, if we want to figure out how to get in there, we could load up LLDB and single step over and 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 over until we hit the Hopper executable. So we know where the entry point is, where it actually executes code. Because again, I forgot to mention, you can't debug Hopper. It kicks you out. And I don't know where they put the deny attach code. I'm assuming it's somewhere in the LLVM framework they attach, because I can't find it anywhere where they would implement something that would kick your process off of tracing it. So mind you, I'm doing this all without really using LLDB as a debugger because it's kind of useless. But I thought, okay, what can we do now to get the entry point? do the step in method over and over and over again. Basically brute force it until we hit it. Well, I'm not going to do that by hand, so what us programmers do is we write a piece of software to do it for us. So what this program does, it's a program I wrote it in Zojo because I need something quick and dirty. What this program does is it loads up Hopper, executes, basically does a step over until it gets kicked out. It remembers the last command it did before the step over. So that way if it gets kicked out, it can restart the process, do step over, get to the point where it got kicked out, do a step in, and then do step over until it gets kicked out again. It's basically just brute forcing until we see the Hopper executable. So if we run this, we can see here, exit found at dynamic library start. So now it's said, okay, we know that now. Now we're going to step into that one. Oh, it got kicked out at the bootstrap start. Okay, we're going to start the process again. We're going to step in the start and bootstrap start. So now it's going to continue on. And it's going to keep doing this forever and ever until it sees the name Hopper. If it sees the name Hopper, it knows this is the point where it comes in. Now this takes about 20 minutes. Again, it's super slow because I'm calling right to the LLDB executable. Oh, here it found another one in dynamic loader underscore main, the C version of main in dynamic loader. So now it's going to start over again, and then the next time it's going to step into main. Well, let's make a long story short. I'm going to close this out. Close all this out. The backtrace ends up looking like this. We see that it goes to start, to bootstrap start, underscore main, initialize main executable, run initializers, process initializers, recursive initialization, notify single, then it calls load images from the libobject-c, Objective-C, and call load methods. Then we can see, oh, it starts skidding into Hopper at this offset off of the mh underscore execute header. So that's from the base of the file plus 556,000 bytes. So since we're still here and we just dumped the memory here, what we're going to do is we're going to do a disassembly, start address. Oh, let me do it because I can't convert hex on the fly. It's embarrassing because I know some guys who can do it really well and I can't. So let me just quick do this. So I'm going to paste this. So 878BF8. So what we're going to do is we're going to 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, 5, 8, 7, BF8. And end, we'll just do 87BC00. Alright, so this is the code that's at that address. Let me see here. Did I do that right? Let me see where we are. 87BF8. Okay, so we got kicked out a little bit after. And if you do this enough, you'll start to see that the actual header here is, or the entry point is right here. This is where you get kicked out. It's at 86C31. This made it a little bit further before the kernel caught up and said, hey, wait a minute, you're not supposed to be tracing this, and then yanks you out. The actual entry, which I got, either way, you basically have to fish around, but you'll figure it out that where the entry point actually happens. 86C31 is the point where this is the first time, as far as I can tell, that a thread actually works its way into the Hopper executable. I mean a thread that is actually executing code written by the people who wrote Hopper. This is the first time. So now, since we can't get a debugger in, the next best thing is to force a library in. So what I did was I wrote a library, and if you want, all you have to do is type in mock-o DLL injection. There's a few methods. My most favorite method is actually adding a load command to the program, and then force the library in that way. And you'll find that on Google. I won't explain how to do that. So I had to write a DLL, and I want to make a DLL that's going to stop. Yes. I wanted to make a DLL that caught right at 8631. That we could insert a command there that would allow us to inspect what's going on. So in Xcode, that's what I did. I created a DLL, and added a constructor so that we could be initialized. And again, and init gets called, since it's a load command, init gets called before pretty much most anything that would happen inside the actual executable, from what I can tell. So in our init command, I did what I said I was going to do. I found the Objective-C load, which is a define up here is 86C31, which is this address here, which is this command here. So we're going to overwrite all this crap here with my own crap. So this is going to patch this address with a jump to this address, which is this function here. So we're inserting an E9, which is E9 is a jump, a relative jump to this function here. Okay? So once that's done, we save the original code too. And it just is a 64-bit uint at that point. We're just dumping, because we only need 5 bytes to jump. A relative jump is a E9 plus a 32-bit integer. So that's 5 bytes. So we're just saving 8, just for the heck, because when I do the patch, or when I do insert the jump, I overwrite 8 bytes, but I only need 5 of them. Anyways, so we're going to jump up to here. So we're going to let this go, and then the next time this enters, it's going to be when that load call happens. So at this point, Hopper's still encrypted, but after this function returns, it'll be completely decrypted in memory. Completely decrypted in memory. So we get the same offset to the load command. We repatch it back to the original code, and then we call it. And once this returns, we'll know in memory we have a totally decrypted file in memory. At this point, we could literally dump the file and we would have the original file back. Obviously, we would have to modify it a bit, to get the binding info reset and all the information reset properly. We'd have to basically realign the executable. It's unimportant at this point. We know that at this point we have the entire executable, so we can look at it. At this point, I dumped it. And if you dump it, let me see if I can open it. Oh, I don't. It's not patched in this version, so let me think here. When I get to here, Fantabulous is basically a dump here. Oh shoot! I should just be running the patch version. Actually, I'm going to. No, this is my patch version. So this is it. This is the Hopper executable. Here are all of this. This is the Hopper executable back to normal. After doing all of that work, you can see we got all the Objective-C stuff back, decrypted, working 100%. All the code works. Everything works in here. And see, everything is working just fine. And we can go in and patch. So that's what it looks like after this function, after the call that load. That's what it looks like. You got the original executable back unaligned, but we, you know, what would be cool would be to actually realign it and have the original executable back. Instead of having the 21 megabyte version of Hopper, have the 5.5 megabyte version of Hopper. Because Hopper is really only 5 megabytes, 5.5 megabytes. So anyways, now that this is done, we're going to insert another shim, and that's at the entry point. Because I want to make sure we patch only when entry is called. We don't want to patch while the dynamic loader is still doing its thing. And at this point, when this function gets called, the dynamic loader is still doing its thing. So I don't want to insert patches when they could get overwritten anyway. So I set another patch at the entry point of the program, which, by the way, would be, now that we have the data dumped, I'll show you exactly where we're patching now, because now at this point, when I'm writing this plugin or this DLL, I know where we are. This is the entry point of the program. This is main. You can see this is a normal stub entry point where this was written by Xcode. It's basically setting up the command line and how many command line arguments there are. This function, you can see it's pulling in two parameters and saving them. Is R15D, if we look, it's EDI, which is the first argument, and EDI means it's 32-bit. And then R14, which is RSI, which is the second parameter, which is a pointer. So we know that this is a parameter, or this is a function that has a signature of integer, comma, two parameters of an integer and a pointer, 32-bit integer and a pointer. So we can write our own function that emulates that, which is this function. And if you inspect integer and the pointer, you'll know that this will say 1 and this will be a pointer to an array. Oop. 1 second. I'm getting phone calls. So now this is the point where we are in main, where the Hopper is finished being decrypted, Hopper's finished being binded, Hopper's finished being everything. We are 100% legitimate, and we are in a set of breakpoint at main. Okay? This is where we write our patch info. This is the patch for it. This basically makes it unregistered, or makes it so you don't have to register. This writes the cracked info in this up here. If you go to Hopper, about this writes this here, and then I add some method swizzling, and what the swizzling will do, allow me to add in the cool stuff. Oh, let me close this down. Let's see. Let me start it up again. The swizzling, what it does is it hooks in and it lets me do cool stuff like this. I can actually call the log window and add strings to the log window. I can add things like add an about menu. So you can actually alter the interface with method swizzling. If you don't know what swizzling is, go ahead and Google it, and it's pretty cool. So I used a class that handles swizzling called JRSwizzle. It's what pretty much everybody uses. And that's it. I think that's about it. So here I do the swizzling. I swizzle NS window controller window did load and put in my own window did load. So we're basically hooking window did load. So that way I know, okay, the window's loaded, I can insert a menu item. And then I hook the NS document init with my own init. And you can see my, where is it? Where the heck is my code? Did I put it above? Oh, I did. Okay. So window did load. What I do is I start up my own Hopper patch stuff, which controls the window for the about menu. And this document saves it calls the original init command and this document commit, and then I know I have a pointer to a Hopper document. So at this point, this is a pointer to a Hopper document. So down here, I can actually call the document, perform selector, log attributed string with message, and then the message. Because we have, since the Hopper document calls this method, we can call it as well, as long as we have a pointer to the right document, and we do because of swizzling. Anyway, that's about it. There's really not much more to it. I guess if you have any questions, go on Kickass Torrents and find me and message me. So that I'm trying to think. I know I left out a lot of stuff because it took me a couple days to really, write this patch. Probably working at it 8 hours every day for about 2 days. Yeah, it was a big pain in the butt. It was fun, and I can't wait to see what they do next because I would love to do this again. Hopefully they update their stuff. So that is Seagull signing off. Have a great day, everyone. Bye-bye.